Alright boys, we are back! We are back on the third day of 30 minutes of problem solving a day. We made it to 3 whole days. You guys better be proud of me, okay? That is some impressive stuff. And honestly, the more I do this, the more hyped I'm getting because I could do all kinds of problem solving. Come on, you guys could give me brain teasers. You guys could make me do like, I don't know, chess puzzle rush, but I'm going to be using Lee Chess because I do not have enough money for a chess.com account. No, I'm kidding. But honestly, there's so many cool things we could do with this series. I honestly hope that it goes well. I probably won't be able to do it after the summer though, so that's a thing. But we're doing some good stuff now, so that is fun. If you guys enjoy the series, please let me know in the comments and I will keep doing it. And I honestly really enjoy the series because it's forcing me to get back into this kind of stuff and it's very fun. So let's just get off what? Go back to where we started, no, left off, on the 2011 AMC 12A problems, and we were on number 20, and we weren't able to solve it in the remaining time, so let's see if we can solve it today. Now, because I know that, like, I don't want to spend too much time on just AMC, I don't want to spend too much time on any one thing in the series, basically, I'm gonna limit myself to 2 more days on this boy, and we'll see how many problems we can solve in the next, hour, and we'll see how it goes from there. So let's turn on our 30-minute timer and we will get started. Okay. Epic. Alright. So basically this problem gave us a polynomial, like a quadratic, right? I should probably zoom in. Okay, there we go. And essentially we want to find this integer k. And last time what we tried to do is we try to add these equations together so that we could get a bound, but I don't think our bound was good enough. Let me just write out the equations again so we could see what we had. And then for 7, we get 49a plus 7b plus c is less than 60, less than 50. Okay, and then next one gives us 70 is less than 64a plus 8b plus c is less than 80. And we want to find a bound on 100 squared of a plus 100b plus c. Okay. So last time what we tried to do is we try to find some kind of combination of these that gives us this, right? So essentially we got x plus y plus z equals 1. We got 8x plus 7y plus z is equal to 100, and 64x plus 49y plus z is equal to 10,000. Okay. So essentially what we try to do is we try to add these equations together so we can multiply these by certain coefficients and get something. So let's just really quickly do it again. So, oh, was I trolling last time? So we did 50. Oh, I wrote that as 63 last time, right? Oh, no. We had to subtract it first. So yeah, okay. I think I messed up last time actually. So let's actually do it again. So we get 63. I actually don't know if we messed up, but anyways, so we got 63 x plus 48y is equal to 9999, and we got 7x plus 6y is equal to 99. Okay, or less or equal 99. Yeah. So essentially when we subtract these, we get multiply the bottom by 8, so we get 99 times 101 minus 8, and then this is that cancels out, and then that's 63 minus 56, which is 7, right? So 7x is equal to that, and then that's 93, and we basically get the same thing as we got before. So x is equal to 99 times 93 over 7. Okay. Then essentially we plug it in here, and we get 99 times 92 over 6, so negative of that, which gives us y is equal to negative 46 times 33. Okay, so we did do it right? We did the right thing, and essentially the first equation doesn't even impact our bound, so we don't have to solve for z. So let us just see whether this gives us a bound. Last time we found that the bound isn't actually useful, so hopefully we don't get the same thing, but let us see. So essentially we multiply this by 99 times 93 times 7, so that's the lower bound, and then we have to add in the lower bound of this one, which gets flipped around because we're multiplying it by a negative number. So we actually have to subtract out 60 times 46 times 33. And essentially we got this some really small number, right? We got we factor out a 33, factor out a what? Can we factor out anything else? There must be something we could factor out, right? I don't remember doing this last time. Maybe, oh shoot, this is a 10. Okay, yeah, that's why. So 330 times 99 times 93, or no, 3 times 93 minus 6 times 46. Okay, so yeah, we get the same thing as we got last time. So it'll give us 279 minus 276. Okay, and that'll give us 3 times 330, so 990. So let us just look at the other bound, but that's probably going to be way too big for anything useful to happen. So we get 80 times 99 times 93 over 7 minus 50 times 46 times 33, right? Yeah, okay. And then we factor out the 330, we get 8 times 3 times 93 over 7, or over 7 we can factor out, minus, oh, maybe it isn't that bad. Okay, let's see. So we get 5 times 46. Okay, right? Oh, times 7. Okay. So, how do we do this quickly is the question. Can we factor out anything? There aren't any common terms, unfortunately. Well, we can factor out a 2, I guess. So this will be a 4 times 2. This becomes a 23. And now I actually think we don't have any more terms. So let's see. 93 times 12 gives us 681,039. And this is a 61111. Okay. That's not too bad. Okay. And then this becomes a 23 times 35, so we could just do 5101007,805. Okay, so the difference between the two is simply what? You get like 311. Okay, so essentially we got 311 times 2 times 330 over 7, which seems kind of big compared to, I don't know, is that big? That's pretty big. That's like on the order of 10 to the 5 over 5. Yeah, okay, that's just pretty big. I don't think that's gonna be useful. Yeah, that's not gonna be useful at all. So let us actually try to solve this in a different way. Maybe that'll help. Huh. Okay, well, okay. So what else do we know? If a plus b plus c is a root, right? So 1 is a root, right? And essentially it is increasing. I'm assuming it's increasing this way, right? So f of 7. Okay, well, I don't know. It's either here. What? What are we supposed to do here? Okay, well, okay, so if we subtract out the last term, we get that 48a plus 6b is between 60 and 50, right? And we know that 63a plus 7b is between, um, like 80 and 70, right? And essentially we want to find what 999 or 9,999 a plus 99 b is between, right? Okay. And essentially we found that this is not a very pretty thing to solve, right? Huh. Yeah, I don't really get the best way to do this. Unless our bounds are good and I'm just trolling. That's also a possibility. 311 times 330 over 7 times 2. Yeah, that's way too big, right? I feel like, yeah. So this is like 10 to the 5, right? And then this is like less than dividing by 5, so that's going to be like at least 10 to the 4, which is too big. Huh. Do we know whether A is positive or negative? Well, okay, so let's say A was negative, right? That means that if f of 1 is 0, that means that this would have to be like, it would have to go up, and how to go up more. I mean, technically? Okay, well, I guess we could kind of assume that A is positive. I'm pretty sure it should be positive, but I don't know if that, I mean, that's not necessarily true, right? Huh. Maybe. Dude, honestly, I have no idea even how to start this one, dude. Like, what could we even try here? Like, we could maybe, hmm, that's actually a very good question. If we can't just add these guys in some form or another, that's not going to be very helpful, right? Um, how else could you do it? Could you solve for these or something? I don't know. Okay, so, like, we know it's 0, that doesn't help us, so we got one root, but we don't know whether any of the other roots work, right? Hmm. Could we subtract these somehow? I don't know. Okay, so let's just say we subtract them, then we basically get, like, well, what do we get? So 8 minus that is 5a plus b is between 10. Could we just subtract them? I mean, then you get like less than 20. It's between 20 and, no, what? Yeah, that's not how, that's not how inequalities work, but basically, yeah, you can't really do that. So the difference is 5a plus b, and you could basically go from like 50 to 80. So this is at like less than 30, but greater than 10. I don't know how that helps though. Huh. How could we even... Huh. I'm actually very stumped. Okay, how much time do we have? I just want to make sure we're not stuck on the same problem. Holy, I spent like 10 minutes on this one. You know, I am going to... Let's just get a hint. Let's see what the strategy is. Okay. Oh, bruh. Oh, it is. It is like doing that kind of thing. Okay. That is kind of smart. Okay. So let us do that kind of strategy. So essentially what they're saying to do is that you want to divide out like the 6, right? And essentially you get like 25 over 3 on that side, and you get 8a plus b, and you get oh, the fact that they're integers actually matters. Oh, huh. Yeah, okay. That's kind of smart. Okay, I did not even think about that. That is something to think about whenever you're dealing with polynomials. If the coefficients are integers, you can have some cool properties. So essentially, the point is this is between 8 and 9, right? And this is less than 10. So the only integer is 9. So we have 8a plus b is equal to 9. So let's see if we could actually solve the problem from here. What about over here? Could we got like 9a plus b is between we divide by 7, right? So between 10 is less than this is less than 80 over 7, which is 11, between 11 and 12. So basically the only possible thing is 11. And then we can literally solve for it. Oh, that's so big brain. Holy moly. Okay, so this actually means that our a is equal to 2, our b is equal to negative 7, and our c is equal to 5. And then we could just plug this in and we should be good. So 200,000 minus 700 plus 5, and that is like 19305, right? So that is between 3 times 5,000 and 4 times 5,000. So our answer should be C. Let's go. I know I didn't solve that one perfectly, but that is how I basically go through these when I am like solving them on my own. If I can't really think of even how to start, I try to get a hint first and then solve it on my own, just so I know the concepts there. Okay, Problem number 21. f1 of x is equal to root 1 minus x. Okay. And then for integers n is greater than equal to 2, let fn of x equal fn minus 1 of root n squared minus x. Okay. If n is the largest value of n for which the domain of f of n is non-empty, let's see. Okay. The domain of fn is C. Okay. What is the value? Okay. So essentially at some point we're going to get to a point where the domain is non-existent, right? So let's just look at the different things. f2 of x. So basically the domain for this guy is x could be any negative number up to like a certain up to 1, right? Because like once you go past 1 you get a root of a negative number, which is illegal. You can't do that. So f2 is fn minus 1, so root 1 minus root 4 minus x, right? So now x could be any negative number. No. So essentially you can't make this square. Okay, so square roots are always positive, right? So essentially this square root can never be like more than 1 is what it's saying. So x has to be at least 3, right? Yeah, and it can't be more than 4, otherwise the inner one would be negative. So now we've limited our domain to 3, 4. Then if we do it again, 1 minus root 4 minus x, or root 9 minus x inside, now we get some more complicated stuff. So let's just start from the inside, right? X is at most 9. But then this square root has to be like less than 4, but yeah, it's like guaranteed less than 4. So we could ignore that. But then we need 4 minus it to be, we need this whole thing to be at least, we need this to be at least 3. Root 9 minus x is at least 3. At least 3? Oh, really? Wait. Huh, what? So if it's at least 3, then doesn't x have to be 0 or something? Oh, because x could be negative, so x could go from negative 7, and then it has to be 0 as the max, right? Because if you go past 0, then this will be like less than 3, right? And then if this is less than 3, then this is going to be greater than 1, and then this thing's going to be negative, okay? So you could go from negative 7, right, up till 0, okay. Oh, so you could basically use the previous one to like recursively determine it, right? So this one is in negative infinity to x, then essentially you want this to x can't go past 4, but it also has to, like, root 4 minus x also has to fall in here, right? So what happens if, okay, so let's just make sure we did that right. So root 9 minus x is less than 4, is less than 3. These are closed bounds actually, whoops. So essentially what we got here is we got that 9 is less than 9 minus x is less than 4, or less than 16, because square roots are positive, and then this basically means that x is what? Yeah, okay, so this is basically what we got over here. Then we got root 16 minus x, and this would basically give us 49 is less than, oh, what? Okay, so this literally has to be 0, right? Because there's no way for root 16 minus x to be a negative number, so it literally has to be x equals 16 in this case, right? Yeah, it's like the only option. Okay. And then once we get to 25 minus x, then what? We need root of 25 minus x to equal 16. So x has to be negative, x is equal to negative like 256 minus 25, which is 231. Yeah, okay. X is equal to negative 231. And then essentially you can't go past that because no square root could equal that. So n was 5, right? N was 5. And then c is negative 231. So negative 231 plus 5 is negative 226. Okay, that was a pretty interesting one. Not too hard, but it is how it is, and it was pretty good. So we got it right. Let's go. Number 22. Let's see what we got. Let R be a unit square region, and n be greater than equal 4, an integer, okay? A point x, I like geometric probability, but we'll see if we get roasted by this one. Probably will, not gonna lie. I have not done this for a while. Let's see, so point x in the interior of y, or R, is called an n-ray partitional. Holy moly. If there are n rays emanating from x that divide R into n triangles of equal area, how many points are 100 partitional, but not 60 partitional? Okay. So let's just think about what partitional means, right? So essentially there's a height here, right? And okay, so it has to be triangles. So you for sure have to like go through here, right? You for sure have to go through there. Otherwise, like they won't be triangles, right? You'll have like some things that straddle the corner, and that's like not good. That'll give you a quadrilateral. That's not good. So we at least need the stuff in the corners. Now each of these triangles has like a certain height, right? The bases are all the same, right? So essentially, we need to like break up the triangles into like into the right number of triangles so that they all have the same area, right? So let us think. Okay, let's just say like the ratio of this to this is R, and this is 1, or like I guess, okay, let's say, okay, this x is xr, and then x plus xr is equal to, okay, so this is like 1 over 1 plus r, and this is r over 1 plus r. And essentially this is like, we'll say r1, and this is like 1 over r1 plus r2. I can write, holy moly, r2, and r over 1 plus r2. Okay, so essentially, are these all relative to each other? Could we like, yeah, so these are the actual heights, right? And then essentially we could just, well, let's see. So basically, like, let's just say that the GCD of like these areas, or like the smallest number you have to divide them into, so that you could all divide each of them into the right areas. Okay, so let's just say like this one has 4 times the area of this guy. Then you have to divide this guy into 4 dudes, right? Then if this is like 4 and 3, 4 to 3, then you have to divide this guy into 3, or you have to divide this guy into 4 and this guy into 3. There's no other way to do it. In which case you need 7 lines. So it has to do with GCD. What's the exact formula? Well, okay, so essentially you need the area of each triangle to be the GCD of like the ratio, right? Like the greatest common denominator, I guess, right? So essentially, like if you have 4 to 3, the GCD is 1. So you essentially do like 4 over GCD plus 3 over GCD, and so on and so forth. I guess like, I guess over here, right, you would have the same idea. I mean, okay, so essentially these fractions could be literally anything, right? Um, just the only constraint is that this fraction has to be 1 minus this fraction, right? Well, I guess. Well, how many rays? So you need 3 rays, 3 more rays in order to partition this one. You need 2 more rays for this guy. Huh. So could you literally get any ratio between like these 4 things? I feel like you could get any ratio you wanted. Okay, this is assume that you could get any ratio you want, right? Then essentially, I mean you probably can't though. Huh. This is actually kind of hard. Okay, we need like a kind of we kind of need like a formula, otherwise we're never gonna get this. How much time have we spent so far? Oh, we only have 6 minutes already. Holy. Okay, we'll just try this one for the rest of the time, and hopefully we're able to solve some of it. So, what do we got? So let's say this is like 3 to 4, and this is 5. Huh, that's actually so annoying. Okay, so let's say we have like a over b, 1 minus a over b, and then we have c over d, and 1 minus c over d, right? And essentially these are just fractions less than 1. So essentially our greatest common denominator is just going to be like, well, let's see. It's just going to be the LCM of b and d, right? And then we're going to basically multiply that. Well, that's how many you want to get to, right? And then how many do you add, though? So the number of rays is like 4 plus, oh, let's just say there's like A to B to C to D, I guess. I don't know. Okay, so let's see. So 1 minus A over B, A over B. Yeah, this is kind of nasty, dude. What the heck? Yeah, honestly, oh, I don't know how to do this one super fast, but we'll see how it goes. So we got like 4 plus D over here, and then essentially we could do, this one's actually kind of tricky. Okay, let's just say as A to B to C to D, right? And essentially the GCD, or the GCD of all 4 numbers is equal to 1, right? So it's basically in lowest form. Then essentially our thing is plus D plus minus 1 plus C minus 1 plus B minus 1 plus A minus 1. So essentially just A plus B plus C plus D. Okay. So essentially what we want is we want the ratio of the areas to be in lowest form, like 100, right? Well, okay, I guess it doesn't have to be lowest form 100. We can multiply it. It could be lowest form 50, but it can't be lowest form of something that's the divisor of 60. So let's see. It has to be a divisor of 100, but not a divisor of 60. Let's just write it out. 1, 2, 4, 5. Any other small one? 10. Okay, so yeah, that's it. So 5, 10, 20, 25, 50, 100. And then we got 1, 2, 3, 4, 5, 6, 10, 12. Holy moly, there's so many factors of 60. God dang it. Then we got 15, 20, 30, 60. Okay, so now we want factors of 100 that are not factors of 60. So these all go bye-bye. Bro, so many. Okay, this one goes bye-bye. And these are the only ones that are left. So what we got to do is we got to find some like numbers A, B, C, D, right? Where these where the sum is like one of these, but it's like, yeah, the sum is one of these basically. So in lowest form. So let us just think about some of this. Like let's say we have like 1, 1. Well, we need 4 numbers. So 1, 1, 1, 23. Is that possible? No, that's not even possible. You basically need 2 of them to sum to the same thing. Because basically, like, you know that this one is going to be half of this one, right? Wait, what? No, that's not how it works. Um well, yeah, because the sum of these heights, yeah, okay. So I'm right. So these areas have to be the same as these areas. So it has to be divisible by 2 then. Okay, so that makes sense. So we could actually cross that out. Then we need 25 and 25, and we need to split that up into like numbers that are GCD 1. So 124 works, right? And then essentially you just make this ratio 1 to 24, 1 to 24. Could it literally be anything then? Yeah, it could. Okay, so yeah, so essentially we just need anything that works over here, 2, 23, and you can't divide it by anything, right? Yeah, you don't want to divide it by anything. Okay. So never going to be divided by 2. It might be divisible by 5 if we do this badly. Like, you can't do 520, 520, because that'll actually be one of these. It'll be 60 partitional, so that's not good. But how do we count all of these fast? So 124 is here, so there's 4 of these guys. And then for the ones that are not symmetric, you basically have like, you basically have, what do you have? You basically have, wait, what? Huh. Well, yeah, for the ones that you, for the ones that like are different, like all 4 numbers are different, then you have 8 possibilities, right? Dude, that's actually hard. What the heck? How do you make sure that the GCD is not 5? Can we use pi or something? Okay, so for 50, the factors are 1, 5, 10. How much time do we got? Let's see. Okay, so I will stop the timer so it doesn't roast you guys, and I will try for a little bit longer, and then we will try again next time, and it will be good. Okay, 24 the Geo. I should actually try that one next time. Okay, so I guess if we get stuck on these 2 for too long, I'm gonna try 24. It looks doable. We'll see. So 1, 2, 2, 5, 10, 25, 50. Okay. So you basically want to subtract out. Well, okay, it has to be 2 or 520, 520. Yeah, so it might actually be 10 partition. So we would have to like subtract out all the 10 partitional things and all the 2 partitional things, or add in all the 2 partitional things. What? Okay, so if we, yeah, so if we can't, we subtracted all the 10 partitional things, that'll subtract out all the 2 partitional things, anyways. Or what happens if we added all the 100 partitional things, and then, oh, but then we have like all this nonsense, dude. Huh. Bro, what? Oh, God. Huh. This is a lot of pi. Okay, so essentially our strategy for next time is to do out this pi stuff. So essentially like 100 counts all of these guys, right? Like if we just do anything that sums to 100, and then we had to subtract out the ones that we don't want, and then add in the ones that we do want. I think if we just think through the pi, it should be doable. But we'll get to it next time. Okay. Thank you guys for watching, although. Oops, I forgot I can't edit this out. God dang it. Okay. Well, anyways, thank you guys so much for watching, though. It's kind of weird doing this not edited, but I hope it was actually entertaining. You guys get to see the non-edited version, exactly how I spend my time. And this is basically what I do when I'm practicing, right? This is like not how I do it in the test. I would probably skip through a bunch of problems, not look through solutions, obviously. So hopefully it was entertaining seeing how I practice for the kind of stuff. But anyways, if you guys have suggestions for future videos, let me know in the comments. Let me know how else you guys want me to do this kind of thing. If I'm doing anything wrong, you guys have any feedback, that would be very appreciated. But anyways, thank you guys for watching again, and see you guys next time. Let's hope we get to day 4. Alright, see ya.